Hello everyone, let's start talking about something a little fundamental, well actually a lot fundamental, and that's dimensions. It's not length, width, and height, it's a different thing. When I talk about dimensions here, what I'm talking about are the foundations of the quantities that we're going to measure. And we need to define those quantities. All right? And the way we've done that is we started off with these three fundamental dimensions. So there's mass. Mass is a measure of a quantity of substance. That's a really crude definition of mass. You can get a better definition from a physics text or a chemistry text, but we're going to go with that. Length is a distance. It's a fundamental measurement of distance. And then time, I'm not even sure how to do that, but there's the three fundamental dimensions that we're going to be talking about in our statics course. Are there others? Absolutely. There's charge or current, depending on how you look at it in electric circuits, and then there's brightness of light, lots of other fundamental dimensions, but these are the three that we're going to be using in our statics course. Mass, I'm going to symbolize that with a capital M, length a capital L, and time a capital T. So we define those as their existence. Okay, let's just leave it at that. There's magic if you want, I don't care. All right, so each of these will have units. There are two systems of units. There's the SI, Standard International System of Units. That's the metric system. And then there's the imperial system or the English system or the American Standard System that kind of all use the same language, but that's where we're going. All right, so the unit of mass in the SI system is the kilogram. All right, and I'm going to symbolize that with kg for kilogram, 1,000 grams. And so there is another system out there called CGS, which almost nobody uses anymore. And then that one, gram, is the fundamental unit of mass, but it's the kilogram. All right, the fundamental unit of length is the meter, and the fundamental unit of time is the second. And each of these has some sort of a definition about how much it is. So for example, the second is defined by the number of vibrations of, I can't remember if it's cobalt or some atom. It's got a specific vibration to it, and it's the time that it takes for so many of those vibrations to take place. Mass, or length rather, the meter is defined based on the speed of light, which is a constant in all reference frames, and how far light travels in a certain amount of time. And then the kilogram is a little bit more exotic. I'm sure there's more modern ways than what I'm used to, so I'm old guy, so I'm going to tell you that the kilogram is defined by the mass of this block of metal, which was underneath a double bell jar in Paris, France. It's not a very nice definition, but that's the way it's defined. There are other ways based on molecular structure or atomic mass, I think it is. And I don't know those real well, so I'm not going to talk about them. In the English system, the unit of mass is the slug. Okay? There's also one called pounds mass, and basically that is the mass of 1 pound of weight, which is a force. It's not one of these, it's a combination of these, right? But if I have 1 pound, 1 standard pound, the mass of that pound is the slug. The difference between mass and weight is subtle, but it's important. My mass here in Casper, Wyoming is the same as my mass in Los Angeles, California. But my weight, because Casper's at 5,000 feet, is different in Casper, Wyoming than it is in Los Angeles, California, where I'm closer to the center of the earth. So mass does not change unless I lose mass. You know, if I eat something, I'm going to gain mass, right? So if I eat something, I've gained mass. But weight changes based on your location. That's why we don't like to use that if we don't have to. So the slug is the fundamental unit of mass in the English system, but pounds mass is very common in your engineering textbooks. Length is the foot. Okay, and I'll use FT for the foot. So 12 inches, you've all grown up with that. But it is more defined than it was when I was growing up. And we'll talk about unit conversions later on. But that's the fundamental unit for length in the English system. And then both the English and the metric system are the same, using the second as their foundational unit of time. All right, so these are my foundational dimensions, and these are the units that go along with them. Everything we're going to use from now on will be based on these dimensions, and then the units will go along with whatever system we're using in the problem. So if I'm talking about something like speed, right, speed is miles per hour, so that is miles is a length and hours is a time, so speed dimensionally is L over T, right? So if I write out something like speed, and I'm going to use V for velocity, if I say velocity and I want to know the fundamental units of that or the dimensions of that, not the units, but the dimensions, I'm going to put it in this, like this double bracket, square bracket thing. And the dimensions for velocity would be L over T. I can do the same thing for other values like force. We talked about weight. Weight is a force. So force, okay, the fundamental units of force are mass times length all over time squared. That's the units of force. Mass times length over time squared. So kilograms, meters per second squared. Kilogram meters per second squared would be the units for force, the fundamental units for force. And then we don't want to say kilogram meters per second squared all the time. And so we're going to call that a Newton. Or in the English system, we call it a pound. Right? So that's how we can give them unit values, but this is the dimensional values. And so this symbol means what are the dimensions of velocity? What are the dimensions of force? And then I would write them out this way. All right, so a couple of things. When I am adding quantities together or subtracting quantities, they must have the exact same dimension, right? I cannot add a speed and a force or a speed and a time. I can't take 5 meters per second plus 10 minutes. You can't add them together. They're completely different creatures. They cannot be added together. So they must be the same dimension. Now I can add 12 feet plus 3 meters. That can be done. I can take a rope 12 feet long, tie on a rope 3 meters long, and I've got a rope with some length to it. That's okay. So adding and subtracting values of different units, but the same dimensions is okay. It's pain, but it can be done. I cannot set two values of different dimensions equal to each other. There's no way for me to convert from 5 meters per second to 7 feet. There's no way to do that. They're not the same dimension, right? So equal signs, adding and subtracting variables or quantities, the dimensions must be the same. Multiplying and dividing, totally different. I can take a length and divide by a time. That's what I've got right here, meters per second. I can take a length and I can divide by a time. That's fine. I can take a mass and times it by a length, multiply it by a length. So mass times length, that's completely legal. And then divide by time squared, which is a different unit, a different dimension altogether. This is okay. Adding, subtracting, the foundational dimensions must be identical. Multiplication and division, I don't have any of those kinds of restrictions. All right, so there's just some rules when it comes to working with dimensions and the mathematical values there. All right, we'll take a look at this a little bit more when we talk about unit conversions. Thank you. If you have any questions, please leave them in the comments below. Thank you.